In the sections we cover from Chapter 8, we're going to do just a quick introduction to the concepts of sequences and series. If you are continuing on toward the calculus sequence, then you're going to need to be familiar with sequences and series and understand how summation notation works and be prepared to use them in depth. If you're not, well, this is just a quick general introduction. We are not going in depth in a lot of things. We're just introducing some formulas and introducing new notation and vocabulary. Don't stress. You're not going to have to remember a bunch of formulas for your exam. You will have to write terms of sequences on your test, find sums, and write general terms. Most of what you can do, what you will need to do for the exam, however, you can do just by working it out and adding them up. You don't necessarily need to memorize the summation formulas, the sum formulas. Okay, so let's start in 8.1 by introducing the concept of a sequence. I've given you 4 different starts of sequences. You have the first 3 or 4 terms for each of them, and I want you to come up with the next 3 terms. Remember, you're just looking for a pattern that you can continue to see what the next terms would be. Pause your video, try all 4, see what you come up with, and then come back and we'll talk about them. Okay, for the first one, I have a series of fractions. 1/2, 1/3, 1/4, 1/5. It looks to me like my numerator's staying 1. It's not changing. And my denominator, I'm adding 1 each time. So my next term would be 1/6, then 1/7, then 1/8. For this sequence, I'm not increasing or decreasing by a set amount each time. I'm literally adding 1 in my denominator. What about the next one? Well, the next one, those next 3 terms would be 18, 22, and 26. How did we get those? Well, hopefully you notice that to get from one term to the next, I'm adding 4 each time. So this one is increasing, and it's increasing by a set amount. In fact, there's a common difference between each term, each consecutive term. What about C? C just has 3 terms given. Can you tell what you're doing to get from one term to the next on C? Well, the next terms on C, I'm having to work them because I can't do them in my head that quickly, should be 54, 162, and 486. Did you figure out how to do that? Well, on C, I'm multiplying by 3 each time. So this is what we would call a common ratio between the terms because I'm multiplying by a factor. 2 times 3 is 6, times 3 is 18, times 3 is 54, times 3 is 162, times 3 is 486. Now D is interesting because you notice I go positive, negative, which means I'm alternating sign. As I'm alternating sign, I'm going to assume I'm going to keep that up. So my next term would be positive and then negative and then positive again. Well, other than alternating sign, what am I doing? I actually have the same common ratio that I had in C. I'm multiplying by 3 every time. So times 3 is 3, times 3 is 9, times 3 is 27. 27 times 3 is 81. 27 times 3 is 81. 81, actually, okay, so I'm not multiplying times 3, I'm multiplying times -3. 1 times -3 is -3. -3 times -3 is positive 9. So I could write it down here, times -3, times -3, times -3. Multiplying by that negative causes my sign to alternate. So when I multiply a negative times a negative times a -3, I get a positive. When I take that positive and I multiply it times a negative, it becomes negative again. So I have a -243 there. And for my next term, it's going to be positive because I'm multiplying this negative times a negative. It's a positive 729. All right, so out of those 4 different patterns, our first one we weren't changing by a set amount. We're just adding a 1 in the denominator. For B, I was adding a value each time. So we had what we were going to call a common difference. And my common difference here is +4. It could have been a negative if it had been decreasing in value. It would have been, could have been subtracting the same thing each time. And these two have common ratios because I'm multiplying by something to get the next term. C, I'm multiplying times 3 each time. So my common ratio is +3 on C. My common ratio is -3 on D. Then we have some definitions. A sequence is just a set of terms that follow a pattern. And a series implies that we're interested in the sum of those terms. I tend to use sequences and series interchangeably. I'm not really good about sticking to one or the other of those. I try to be very clear, though, where letting you know when I want you to find a sum. The general term is written as A sub n, A with a subscript n, where that n tells you which term in the sequence. For example, A sub 5 would be the 5th term of the sequence that I'm interested in. Let's do the 5th. Let's do a few of them. Let's do A, B, C, D. I want you to give me A sub 5 for A sub 3 for B, do A sub 1 for C, and do A sub 7 for D. Give me those values if you would. Well, look back up at your 4 sequences at the start. For the sequence A, the 5th term, 1, 2, 3, 4, 5, was 1/6. For sequence B, the 3rd term, 1, 2, 3, is 10. For sequence C, the 1st term is 2. And for sequence D, the 7th term, 1, 2, 3, 4, 5, 6, 7, was 7/29. So that subscript just tells us which one of the terms we're interested in. If I just say A sub n, that's what we call our general term. If we know our general term, then we're able to find any other term in our sequence. When we have a sequence, that sequence will either be infinite or finite. If it's infinite, I can express it as A sub n in fancy braces there. I'm talking about a function whose domain is the set of all positive integers. So I have A sub 1, A sub 2, A sub 3, A sub 4, all the way to A sub infinity. I have a set of terms that never ends. How could I show that D, right here, how could I show that D is an infinite sequence? Well, if I want to show that a sequence is infinite, I put an ellipsis at the end. So I could say, and we're not going to list out all 7 of those terms for D, but I could say 1, -3, 9, -27, and then after that last comma, I could do ... And that just shows that this sequence extends forever. So if I see that ellipsis at the end, I know I have an infinite sequence. A finite sequence, on the other hand, has a set number of terms. It has an ending point. It could still have a lot of terms. It still have 500 terms, 27,000 terms, but it has a set number of terms. It's not going to go on and on forever. Something that you're going to see with your sequences and series a lot is factorial notation. I think that we've already introduced factorial notation this semester, but I teach it in other classes, so I can't be sure. So we're going to introduce it here. Factorial notation, and that should be underlined to follow our pattern. Factorial notation for any positive integer n in factorial, and that's how I read that. I read that as n factorial, is defined by, and then whatever n is, I multiply by it, and then I count my way down to 1. So for example, if I have 5 factorial, that would be 5 times 4 times 3 times 2 times 1. And the result is 5 times 4 is 20, times 3 is 60, times 2 is 120, and anything times 1 is itself. So that comes out to be 120. Now, smaller factorials are pretty simple just to calculate either in our head or using our calculator. What if we had something big? What if we had something like 27 factorial? Well, I'm going to start at 27 and I'm going to count my way down, multiplying to 1. But that's going to take a while, and if I'm trying to do all those numbers, the multiplication by hand in my calculator, I'm likely to make a mistake. So I want to encourage you to find your probability button on your calculator. PRB means probability. If I want to find 27 factorial, I'm going to enter 27 and then push that probability button and move my cursor over to the exclamation point because that means factorial. So here I have 27 factorial. And it gives it to me, but notice it has to give it to me in scientific notation because my screen is not large enough for this number. This says times 10 to the 28th, which means I need to move my decimal place 28 times to the right. So that's a really, really big number, 27 factorial. Let's go ahead and we'll record it as 1.08 and then what's the best way to do? Well, yeah, I'm not going to write all that down. Approximately, let's approximate it. 1.089 times 10 to the 28th power. That's an approximation of 27 factorial. Let's see if we do, let's do 15 factorial. Let's see if 15 factorial is something that's large, and yet we could record it because it doesn't give it to us. That still gets us scientific notation. See, these numbers get really big really, really fast. 9 factorial. There we go. 9 factorial is manageable. 362,880 is 9 factorial. Okay, what if I have something like 10 factorial divided by 8 factorial? Well, the nice thing about factorials is that I can simplify them really well. Think about numerator and denominator. If I were going to list all of these out, I would start at 10 in my numerator and count my way down to 1. If I were going to start in my denominator, I would start at 8 and count my way down to 1. Well, 10 factorial is bigger than 8 factorial, right? So 10 factorial would be 10 times 9, and then I could say times 8 factorial. Because 8 factorial includes 8 times 7 times 6 times 5 times 4 all the way down to 1. That means that if I'm doing this division, those 8 factorials are going to cancel out, and I'm really just left with 10 times 9, which is 90. Okay, then the final problem I have for you here is 0 factorial, and that's kind of a definition. 0 factorial is defined as 1. Now we do that because it fits our pattern. When we use factorials, we're talking about arranging sets, how many different ways you can arrange sets. Well, if I have 0 things, I can only arrange those 0 things one way. So 0 factorial is defined as 1. 1 factorial is also 1, if you're wondering. Let's look at the next page. Okay, so we have an example here. And we want to come up with the sequence. We have a sequence where we're given the general term. Our general term a sub n is n over n plus 1. And we're asked to find values for n is 3 to 7. Remember, n is the number of the term that we're interested in. So if we're asked to find where n is 3 to n is 7, I'm finding the 3rd, 4th, 5th, 6th, and 7th terms because it's or equal to. I include the 3, I include the 7th term. I don't care about the 1st and 2nd terms. I don't care about the 8th, 9th, 10th, or 137th terms. I just want these terms from 3 to 7. So I'm going to find a sub 3, a sub 4, a sub 5, 6, and 7. I know where to start and I know where to stop because of this notation. Find from n is greater than or equal to 3 to less than or equal to 7. All right, so this tells me which 5 terms I'm finding. This general term tells me how to find it. What I'm looking for, the general term, puts n in the numerator and n plus 1 in the denominator. So if n is 3 for my third term, I have 3 over 3 plus 1, which is 3/4. If n is 4, I have 4 over 4 plus 1, which is 4/5. You see the pattern? 5 over 5 plus 1 is 5/6. 6 over 6 plus 1 is 6/7. And 7 over 7 plus 1 would be 7/8. Now, I don't have to go in order. I could ask you to give me the 103rd term. And you'd say, okay, well, this is n. That would be n over n plus 1. The 103rd term would be 103 over 104. Because it follows this pattern. It doesn't matter which term I'm asked for. I can just go find it. Now, that's not the case for a recursion formula. The recursion formula works a little bit differently. It's a recursion formula if I have to know the term right before it. Okay, so with the recursion formula, like I said, we have to know the term just before it. Whenever you have a recursion formula, you're going to have this notation a sub n minus 1. When you see sub n minus 1, you always immediately need to think to yourself, last term, whatever I just found. Now, because it defines that nth term as a function of the previous term, the one right before it, I've always got to know the one right before it. For this general term, this is not recursive. That's not a recursive definition. I popped out this a sub 103, the 103rd term, without having to know the 102nd term, or the 101st, or the 100th, etc., all the way down to the first term. I could ask for any term I wanted and just give it to you. But with a recursion formula, I have to go in order, because to get the 103rd term, I have to know the 102nd term, because that a sub n minus 1, that previous term, is always going to be part of the definition. Okay, here's an example of our recursion formula. What are the first 4 terms of the infinite sequence in which, and then I'm given some information. So I'm asked to find the first 4 terms. That means I'm going to need a sub 1, a sub 2, a sub 3, and a sub 4. I'm not asked for something like a sub 20 or a sub 37 because I would have to find all of them up to that since it's a recursion formula. Okay, here's the information I'm given. First, I'm told my first term. If you have a recursion formula, you are always told your first term because there's no way to discover it. So a sub 1 is 3. That's what it is. I've got to have that starting place. Then I'm given a general term that applies for everything else. For n greater than or equal to 2. So for my second term on toward infinity, because it says it's an infinite sequence, from the second term on, I'm going to use this formula. My formula says previous term squared minus 5. Well, if I'm looking at the second term, the previous term was 3. So that would be 3 squared minus 5. Well, 3 squared is 9. 9 minus 5 is 4. So my first term is 3. My second term is 4. When I'm finding the third term, I think previous term squared. Well, this now is previous. So previous term squared minus 5. 16 minus 5 is 11. Now when I'm finding the fourth term, that third term is my previous term. You start to get the hang of it? So previous term squared minus 5. 11 squared is going to be 121. And 121 minus 5 is 116. And that's my fourth term. So you see, I can keep going forever, but I can't just jump in there and get a term in the middle of the sequence somewhere without knowing the term right before it. You know what? I'm going to go in and I'm going to change that to previous term because that's the way I like to say that. All right, let's look at the next notation that we're introduced to, our summation notation. Anywhere we see this sigma, this big, kind of looks like an E, it's a Greek sigma, we know we're asked to find a sum. The summation notation tells us to find the sum of, in this case, the first n terms of a sequence. Now let's talk about our pieces of our summation notation first. At the bottom, below the sigma, we see I equals 1. This is what we call our lower limit of our index of summation. I is our index of summation, and then bottom is the lower limit. That makes sense, right? Because it's low. And on top is the upper limit of that index of summation. Well, our index of summation tells us which terms we are going to sum up. So this gives me my starting place, which term I start with, and this gives me my stopping place, which term I end with. My index of summation does not have to start with the first term, so make sure you pay attention to that. It could be I equals 3 to 10, and then I would want to know the third term all the way to the 10th term. Right now it just says I equals 1 to n, so I have, I can fill in the blank with that. Then I'm given my general term, how to find each term according to which term it is. And I say, okay, that's going to be equal to the sum of that list. Let's do an example of these. It says to find the sum of the squares of the first 5 positive integers. So we're going to set up our index of summation with our big sigma. There we go. Our lower limit is I equals at the bottom, and we're finding the first 5, so we're going to go from 1 to 5. There's my index of summation that indicates I'm finding the first 5 terms. Remember, if I didn't want to start with the first term, I could say the 4th through the 9th terms, or the 2nd through the 27th terms. It doesn't really matter, but my lower value would go here, my starting place would go here, and my upper limit would be here, the last term I'm interested in. And then for the general term, I want to square those integers. Well, the integer is the I, so my general term is just I squared. So what is that going to look like? Well, I need to find from 1 to 5 squared added together. So I need 1 squared plus 2 squared plus 3 squared, plus 4 squared, plus 5 squared. And I know to stop here because I goes from 1 to 5, lower limit to upper limit. General term is taking that I and squaring it. Okay, 1 squared is 1, 2 squared is 4, and then I have 9, 16, and 25. And when I add all of those together, I have a 10 here, 9 plus 1 is 10, 4 plus 16 is 20, 10 and 20 is 30, plus 25 is 55. So this index of summation, the answer I'm looking for is this 55. Okay, let's look at the next page. We have one more example of an index of summation. This time I'm asked to find the 1st through 6th terms, and my general term is just 3. Well, when your general term is a constant, that's just it. You're just talking about that constant. It doesn't matter which term it is, it's going to be 3. Well, how many terms am I going to add together? The 1st through the 6th tells me I have 6 terms, and each term is going to be 3. So that ends up being 3 added to itself 1, 2, 3, 4, 5, 6 times. Well, 3 plus 3, 6 times, same thing as 3 times 6 would be 18. That's just a little bit of a special case when we have our general term is a constant. Let's move on to section 2 and talk about arithmetic sequences and series. So in section 1, we were talking about any kind of sequence or series. It could look like anything. Those first 4 we started with, we just found the pattern. We were not focusing on a particular type of pattern. When we talk about an arithmetic sequence or series, however, we're talking about the sequence or series in which there is a common difference between terms, between consecutive terms, excuse me. So if you look back at those first 4 sequences, B is an arithmetic sequence because it has a common difference. To get from one term to the next, I'm adding 4 every time. Now that common difference can be positive or it can be negative. I can be adding the same amount every time, or I could be subtracting the same amount every time. Another example of an arithmetic sequence might be, let's do 25, 20, 15, 10. Well, what would be next in that arithmetic sequence? If I'm looking for my next 3 terms, well, it would be 5, 0, -5, and then I could just keep going, right? This could be an infinite sequence. I know it's arithmetic because I have a common difference between every consecutive term. I am adding a -5, or I'm just subtracting 5. So my difference between each term is a -5 here. My general term for an arithmetic sequence or series, remember sequence is when I'm just looking at the terms, series is when I'm thinking about adding them together. The general term, a sub n, is equal to that first term plus n minus 1, and then in parentheses, times d. So I'm going to have to clean this up some to get it in simplest form when I'm using it. But n is the number of terms. A sub n tells me how many terms. A sub 1 is the first term, and d is my common difference. So a sub 1 is the first term, my first term. N is how many terms there are, and d is my common difference. Okay, find the general term, a sub n, and the first 4 terms, and the 30th term. So I have 3 things I'm being asked to do. Find the general term, the a sub n, the first 4 terms, and the 30th term. So let's start by finding our general term, a sub n. Well, we know that for an arithmetic sequence, we are told that our general term, a sub n, is equal to first term plus the quantity n minus 1 times d. I'm given my first term is -7, so a sub n equals -7 plus n minus 1. I haven't been told how many terms there are, so I just leave that as n, times d, my common difference, which is 6. Well, I'm going to use order of operations here. So I'm going to distribute. That gives me -7 plus 6n minus 6, which if I put those in order with the constant last after combining like terms, my general term is 6n minus 13. So that is the general term that will give me this sequence of terms that I'm interested in. Now we can double check ourselves to make sure that this general term gives us the first term we were told to expect. If I find, my second part is to find those first 4 terms. So let's just go ahead and do that. If I find a sub 1, using this, I have 6 times 1 minus 13, which is -7. That was the first term I was told to expect. So I need to find the first 4 terms, and then I'm going to find the 30th term. Okay, so that was our first term. Let's do 2, 3, and 4, plugging into the general term. Now, if we plug in 2 where we have an n, we have 6 times 2 minus, not equals, minus 13. 6 times 2 is 12, minus 13 is -1. So that would be my second term. My third term, if I use my general term here, I plug in 3 for n, so I would have 6 times 3 minus 13. 6 times 3 is 18, minus 13 is 5. And then my fourth term would be 6 times 4 minus 13, or 24 minus 13, which is 11. Now let's think about this. Let's think about this and work this through. If I am doing consecutive terms, as long as I know that common difference, I can just apply that common difference every time instead of plugging into the general term. I could have said, okay, -7, and then I go to -1, and then I go to 5. Well, it looks like each time I'm adding 6 here. And you know what? That's what I was told. Common difference is 6, which means 5 times 6 is 11, and 5 plus 6 is 11, and 11 plus 6 is 17, and I could keep finding terms that way. The last piece of information I'm asked to give, however, is the 30th term. And it would take me a while to work my way from the 4th term to the 30th term. So in this case, it's really nice that this is not a recursion formula. And we do have a general term. So my general term is 6 times n. So this time it's 6 times 30 minus 13. Well, 6 times 30 is 180. And 180 minus 13 is 167 as my 30th term. For these consecutive terms, I don't really have to go back and use that general term every time, but we got some practice with how to use it. If I'm going to jump down the list and I don't want to do all the consecutive terms, then it's super helpful to have that general term so I can just plug in and figure out what it would be. Let's do our second example. For this next example, we're given n equals 2 to 8. So we're finding the 2nd to the 8th terms. We're not asked to find the first term. We're not asked to keep going after 8, except we're also asked to find the 30th term. So we're going to find the 2nd to the 8th terms and the 30th term. We're given not the difference in the first term to make that general term, but we're given the general term itself. So let's set this up. We're going to find the 2nd through the 8th term. So a sub 2 all the way through a sub 8. And then we also need the 30th term. Okay, so plugging into our general term where n is 2, we have 2 times 2 plus 1. 2 times 2 is 4 plus 1 is 5 for our 2nd term. Our 3rd term would be 2 times 3 plus 1. So that would be 6 plus 1 is 7. I bet it's 2 is our difference. So our 4th term, 2 times 4 plus 1 be 8 plus 1 is 9. Yep, look at that. I've got a common difference of 2. Which means my first term that I wasn't asked to find would have been 3 because I would go subtract 2 to get backwards. Plus 2 plus 2. My 5th term is going to be 11. My 6th term would be 13, then 15, then 17 to get to my 8th terms. Notice I did not go back and plug into that general term each time. I identified what my common difference was, and I just added on. I'm not going to do that adding on business to get to the 30th term because I would have to go from the 9th term all the way to the 29th term, and I don't want to do that. For the 30th term, I am going to use that general term, and I'm going to plug in n for 30, add 1. So my 30th term is going to be 61. Okay, let's look at how to find the sum of a series, arithmetic series. The sum of an arithmetic series is found by using the first term, a sub 1, the nth term, which is the last term we're interested in, and plugging it into this formula. S sub n is my sum, and that tells me how many terms I am summing, how many terms I am going to be adding together. I take that n, that number of terms divided by 2, and I multiply that by the sum of the first and last terms. Now, basically what this is telling me to do is to find n times the average term. Think about how you find an average. Well, if you had 2 test grades, you would add them and divide by 2. Well, that's what we've done. We divided by 2. Except that we're taking the first and the last terms, adding them and dividing by 2 to find the average of the first and last, and then we're multiplying it by how many terms there are. This works because of the common difference between terms. This only works because of the common difference. Okay, I have a question for you. This formula implies that we have a finite series, or at least we're only interested in summing a finite set of terms. Could you find the sum of an infinite arithmetic series? Well, let's look back at that last arithmetic series that we had where we were adding 2 each time. If it goes on to infinity, what's going to happen to each term? Well, each term increases by 2, which means every time I add another term to my series, that sum is going to keep increasing. If I had a common difference that was negative, it's going to go to negative infinity. And it's going to keep getting small. The sum is going to keep increasing in a negative direction. So if I have an arithmetic series, I can't find the sum of an infinite number of terms because it just keeps increasing without bounds. And it can keep increasing in either a positive or a negative direction. Without bounds means it never stops. It doesn't have any boundaries. An infinite arithmetic series is going to have a sum that just keeps getting bigger and bigger and bigger and bigger, either in the positive or negative direction. It's never going to stop getting bigger, so I cannot find the sum of the infinite number of terms. I can, however, find the sum of a finite number of terms in an arithmetic series. This is how I would find that sum. Now remember, I said for the test, you don't have to memorize this because I'm never going to give you a sum to find that you couldn't just add up all the terms. This one's a little large. This says to find the sum of the first 15 terms. Well, how do I know I want the first 15 terms? Because my index of summation is from 1 to 15. So I want to find the sum of the first 15 terms of this series, 3i minus 5. Well, if I want to sum this is the formula I'm going to use. S sub n equals n over 2 times a sub 1 plus a sub n. And I'm finding the sum of 15 terms. So this is s sub 15. And anywhere I have an n, I've got 15. So 15 divided by 2. Now to fill in the parentheses, I need to know the first term and I need to know the 15th term in this case. So the first term, well, a sub 1 is going to be 3 times 1 minus 5, because where I is 1, which is 3, I don't need parentheses there, sorry. 3 minus 5 is negative 2. My first term is negative 2. What about my 15th term? Well, a sub 15 is going to be 3 times 15 minus 5. 3 times 15 is 45 minus 5 is a positive 40. So I plug that into my formula. So the sum of the first 15 terms of this series is going to be 15 divided by 2 times 38, because negative 2 plus 40 is 38. Now I have some stuff going on here I can do in whichever order I want. I could do 15 times 38 and then divide it by 2. I could do 15 divided by 2, it gives me 7.5 times 38. Or I can say 38 divided by 2 and then multiply that by 15. Whichever way I choose to do it, I end up with 285. Let's do another example of this. Find the sum of the first 35 terms for the series when I have this general term, a sub n equals 8n minus 2. I'm summing the first 35 terms. So s sub n equals, and then I'm going to have 35 over 2, because in my formula it starts as n over 2, times, I need my first term and my 35th term. So let's come over here and let's find our first term and our 35th term. My first term is 8 times 1 minus 2, or 6. My 35th term is 8 times 35 minus 2. I'm going to have to pull out the calculator for that. And I have 8 times, I got my calculator button wrong. 8 times 35 is 280 minus 2 comes out to be 278. So I plug that in there. And 6 plus 278 is 284 times 35 ½ Well, half of 284 is 142. So that sum is going to be 35 times 142. However I want to work that out, I should get a sum of 4,970. Okay. One more example. Find the sum of the first 20 terms for the series when you're given the first term, 3, and a common difference of 2. Okay, well, I know that when I'm finding the sum, I know that when I have common difference, that means I have an arithmetic series. And I know when I'm finding the sum, I need S sub n equals n over 2 times the first term plus the nth term. I'm summing the first 20 terms, so that is S sub 20 equals 20 over 2, and I need the first term and the 20th term. Well, the first term is given to me as 3, so that's good, but I need the 20th term. I need A sub 20. To get that, I've either got to go through and I've got to start at 3 and subtract 2 until I get to the 20th term, or I have to do my general term for an arithmetic sequence. My general term for an arithmetic sequence takes the first term plus n minus 1 in parentheses times d. Well, my first term is 3 plus n minus 1 times a negative 2 for my common difference, which gives me, when I distribute that, 3 minus 2n plus 2, which is a negative 2n plus 5 as my general term. Once I have my general term, then I can find my 20th term. So I have negative 2 times 20 plus 5. Negative 40 plus 5 is a negative 35 for my 20th term. So I have 3 and a negative 35 that I need to add together. 3 and negative 35 is a negative 32, and 20 divided by 2 is just 10. So my sum then is a negative 320 for the first 20 terms of that arithmetic series. And again, I knew it was arithmetic because it had a common difference. What about geometric sequences and series? This is the last set of topics we're going to talk about in Chapter 8, geometric sequences and series. If I have geometric sequences in series, then I know that I have a sequence or series in which there is a common ratio. Common ratio between consecutive terms. And there's my general term for my geometric sequence and series. If you look back to the very first page of notes, we had C and D were both geometric sequences because they had common ratios. The common ratio in C was a positive 3. I was multiplying times 3 to get the next term. And the common ratio in D was a negative 3. I was multiplying by negative 3 to get the next term. Okay, so we have the first term, a sub 1, times the common ratio to the n minus 1 power. This says to find the general term, a sub n, of this geometric sequence. Well, first of all, let's identify the common ratio of this geometric sequence. I know that my first term is 1 because it's right there. What am I doing to get the next term each time? Well, I'm multiplying by a positive 5. That means my general term, when I use this formula, would be a sub n is 1 times my common ratio of 5 to the n minus 1 power. And that's just it. That's what it is. Notice the structure difference between a geometric sequence and my arithmetic general term. When I have an arithmetic general term, I'm going to have something times n plus or minus a value. When I have a geometric general term, I'm going to have something raised to a power. That's where I get that common ratio. We're not going to do very many examples as part of the notes. We have a practice packet that we're going to do instead of examples as part of the notes. Okay, the sum of a finite geometric series. Now remember when we were doing arithmetic series and finding sums, we discussed the fact that you could find the sum of a finite arithmetic series, not an infinite. But notice on this page, I have it set up to find the sum of both finite and infinite geometric series. To find the sum of a finite geometric series, I'm going to use this formula, where I have a first term a sub 1 and a common ratio r. This n, again, tells me how many terms I am adding up. Let's find the sum of this finite geometric series. So I've got s sub n. I'm finding my index of summation is 1 to 6. So s sub 6, I'm summing 6 terms. And then I have a ratio over here. I need to know my first term, I need to know a sub 1, and I need to know r. Well, if you think about your general term, this is a sub 1 times r to the n minus 1. Now, notice that I don't have an exponent of n minus 1, which tells me that this 3 is not going to be my first term. I can't expect 3 to be my first term. I can, however, expect 2 to be my ratio. So let's find my first term. My first term would be where I is 1. So I have 3 times 2 to the first power. 3 times 2 to the first is just 6. Notice that since the exponent is not n minus 1, or I minus 1, 3 is not my first term. My first term is 6. Times 1 minus, and we said that our ratio is going to be 2. If we want to double check that, I could find the second term. It would be 3 times 2 squared. Well, 2 squared is 4. 4 times 3 is 12. Yep, look at that. 6 times 2 is 12. My third term would be 24. I could check another term if I wanted to be certain. In fact, if I wanted, I could find all 6 terms and add them up to get the sum. But we're going to practice using our formula. 1 minus r to the n. Well, r is 2 and n we said is 6 because that's how many terms I'm summing, over 1 minus r. Well, my denominator is easy. 1 minus 2 is a negative 1. My numerator is going to be 6 times 1 minus, what is 2 to the 6th? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, that would be 64. So in my numerator, I have 1 times a negative 63 divided by a negative 1. My numerator is going to be negative divided by a negative denominator. So what I really need to know is what is 63 times 6? That comes out to be 378. If you don't trust this sum equation, just find your 6 terms and add them up. So there's more than one way to approach this. The sum of an infinite geometric sequence. Well, you cannot always find the sum of an infinite sequence, right? In fact, if my ratio right here is more than 1, either positive or negative, more than 1, then that means my series is going to have no sum, just like an arithmetic series, because that series is going to increase or decrease. It's going to get large either in a positive or negative direction. It's going to increase or decrease without bounds. It's just going to keep getting bigger and bigger and bigger and bigger because I'm multiplying times 2 or times 3 or times negative 5, but it's going to keep getting larger, so I can't find that sum. However, if my ratio is less than 1, positive or negative, that means if the ratio is a fraction, proper fraction, less than 1. So if the ratio is a proper fraction, 1/2, 1/3, 2/5, 3/7, if that ratio is a proper fraction, positive or negative, then I can find the sum because each time I multiply, make it easy. If I start with 100 and my ratio is 1/2, well, 1/2 of 100 is 50. 1/2 of 50 is 25. 1/2 of 25 is 12.5. And it keeps getting smaller and smaller and smaller. I can find that sum. And I find that sum by, if you look at these two equations and compare them, I'm simplifying it because this, since my ratio is a fraction, it gets infinitesimally small. So that's like this just multiplying times 1. I just have first term over 1 minus r, 1 minus that common ratio. Now, rather than do an example of this here, we're going to switch to the practice packet.